observed it. And I must thank Professor Mishra, Professor Omkar, and all of my colleagues here for calling me to give this lecture. Professor Omkar just took me on a very emotional trip. I went around the lab, saw the room where I gave my first scientific presentation, my first seminar. That was, believe it or not, 50 years ago, exactly 50 years. In 1973 it was. And it was on, that topic was inert gas compounds. So there are just a few compounds of inert gases that exist in nature. In fact, they are not natural. So they are all synthetic compounds. But the element that I am going to talk about today has unprecedented compounds, which are produced by nature, by the biota. I am going to talk about carbon, which is the key element for life. And as you know, biota produces millions of organic compounds which play a very important role in life processes. And they store energy in the form of food and fuel that we all consume. And carbon is the backbone of life on Earth. We are made of carbon, we eat carbon, respire carbon, and our civilizations, our economy, our homes, our means of transport, all built of carbon. It's very important. But that's not something I'm going to talk about. I'm going to talk about this aspect. Carbon also plays the central role in regulating Earth's temperature, the climate, making it suitable for the origin and sustenance of life. And that is something that I'm going to be dealing with today, this afternoon. Okay, the role that it plays in controlling the global climate is evident from this slide, which gives a comparison between the conditions that exist on Earth and Venus. And these are basically twin planets. Venus and Earth are twin planets, in the sense that they are roughly of the same size, same mass, density, chemical composition, and gravity. But they are not identical twins, as you can see, because they don't look identical. The Earth is a blue planet, and the other planet is called the morning star or the evening star. In fact, it's the third most luminous object in the sky after the sun and the moon. There is one major difference between these two twins. On Venus, all the carbon that by the way, I must mention that because they are roughly of the same size and same chemical composition, they are estimated to contain roughly the same amount of carbon. On both planets, we have roughly the same inventory of carbon, but the major difference is that all the carbon on Venus is in its atmosphere. Everything is in the atmosphere, and it's not the case with the Earth. The Earth's atmosphere contains only about 0.042% carbon dioxide in the form of carbon dioxide. It's 0.042%. In the case of Venus, it's 96% carbon. So it's almost entirely purely carbon dioxide. And because all the carbon is in there, the atmosphere, the atmosphere of Venus is very dense, and the pressure is about 100 times that we have in our atmosphere. Because it's so dense, everything is packed in there, all the carbon there is in the atmosphere. And because of this carbon dioxide, huge quantities of carbon dioxide in the atmosphere, there is super greenhouse effect. And the surface temperature on Venus is scorching 470 degrees Celsius. And that's why it's so luminous, so bright. You can see it when there are no other stars seen in the sky, you can still see Venus. Okay, and the other thing is that the most important thing in my view is that we have oceans, Venus doesn't have any ocean. So the Earth is the only object in fact celestial body that we know that has huge quantities of liquid water. Okay, so we have oceans and Venus doesn't have. And because we have oceans, we have life, and there doesn't exist any life on Venus either. So these are the important differences. But you may ask that where is the carbon on our planet? It's bound in the form of carbon. All the carbon, in fact 99.999% of carbon on our planet is in the form of sedimentary rocks. Carbonates like marble, chalk and what have you. All the carbonates that we have, all the carbon we have is locked up in the sedimentary rocks, in the rock, in the form of rock. Is 99.999%. Almost everything is in there. Okay? There's some point less than 0.001%, which occurs in the form of oceans, fossil fuels, soil organics, land biota, atmosphere, and so the atmosphere, actually, our atmosphere contains very little carbon. And that's something I would like to emphasize, that this pool is really very, very small. Now, how did that carbon get in here? Is because of the fact that we have oceans and carbon dioxide is highly soluble in water. So this carbon dioxide was sequestered from the atmosphere very early during the life of our planet, in the first few hundred million years. As the earth cooled down, the oceans were formed, the CO2 was removed through solution, and then carbon dioxide, that carbonate combined with calcium to form inorganic calcium carbonate, and that inorganic carbonate was eventually recycled. And today we have carbonate rocks which are mostly biogenic. They are biologically produced. They are not chemically precipitated, but biologically produced. So I'll come back to the fact that we have very little carbon in the atmosphere. In fact, it's close to 0.9 units are billion tons of carbon. So this used to be actually 0.6. It has gone up to 0.9 because of human activity, because we are releasing a lot of carbon to the atmosphere. So there are people who ask, and this was the motivation for me to give this talk. On our WhatsApp group, there was a message that was shared. It said that there is so little carbon in our planet that it's not important. And so I said that I would like to give a talk on this. In fact, everything that I'm going to talk about is not my work. None of it is my work. I work on related topics, but not exactly on this topic. So, but I chose this topic because it is very important, firstly. And secondly, there is a lot of misconception among people because they think that, there is not much of carbon in the atmosphere, so it's not very important. And the very fact that there isn't a large amount of carbon in the atmosphere is very important. Why is it not there is the reason. Why the increase by 50% in the atmospheric carbon CO2 pool is so important. That's something that I'm going to talk about in the rest of my talk. Okay, so here is, let me tell you something about carbon dioxide. Carbon dioxide is a very important greenhouse gas. So even in traces, it affects our climate. It's very important greenhouse gas. You all know, I'm sure you all know about what is the greenhouse gas. These are gases that actually trap back radiation from the Earth's surface, which is in the infrared range. And I'm going to talk about it a little later. So here is a record. Here are a couple of records of atmospheric temperature on the planet. And carbon dioxide content of the atmosphere, and this goes back to about 400 million years. So we are talking about geological time scale. Well, you may ask me who measured carbon dioxide at that temperature 400 million years ago. There was nobody holding a thermometer to measure the temperature at that time. So these things are actually recorded from proxies, derived from proxies. There are numerous proxies in the sediment or in rocks that you can be used for determining the CO2 content of the atmosphere and the temperature of the atmosphere. There are also data which are actually based on direct measurement, not instrumental measurements, which only exist for the last maybe 70 years or so, maybe a century or so. But there are also measurements of CO2, for example, which are derived from analysis of polar ice, and I'm going to talk about it later in this presentation. So here are two records of temperature, that's the upper panel, and CO2, which is the lower panel. And I must point out that the scales are different, in fact, in these two panels. Here the scales are logarithmic, not linear, okay, and in the upper panel they are linear, okay. So, and they are not continuous records. They're basically records of 4 different time periods, okay. So this is one, this is the second one, this is the third one, this is the fourth one, all extending back to 400 million years. So CO2 content of the atmosphere is determined by the balance between carbon sequestration, the carbon which is taken up from the atmosphere through ocean exchange, it's soluble in water, so it goes into solution. Plant uptake, the plants require carbon dioxide for their growth. They convert inorganic carbon into organic carbon. Sedimentary burial, as the organic matter sinks, it gets buried in the sediment. Weathering is the solution of rock, disintegration of rock. So these are the streams for carbon dioxide. And the sources are emission from volcanic activity, from volcanoes, decomposition of organic matter, including the remains of animals, and so when I die, organic matter will be degraded, and the carbon comes back to the atmosphere. So the balance between these sources and sinks determines how much carbon dioxide remains in the atmosphere, and that amount varies with time. As you can see here, the concentrations have been changing. This, by the way, as I said, is the logarithmic scale. Okay, so this is 2000 ppm, which is 0.2%, only 0.2%, 0.02%, in fact, is the 2 per mil. 2 per mil or 0.02% is the maximum. So the CO2 concentrations, even at the highest levels, did not exceed about 0.2, 0.3, 0.02%. Okay, so that was the maximum that we have. Today we have 0.041 or 0.042. But the maximum it was only about 0.02 or 3. Okay, so these are the concentrations in ppm, and here's the time going back to 400 million years. And CO2 variability is similar to that of temperature. As you can see, these records are visibly similar. But you must remember that the scales are different. This is logarithmic scale, and this is linear scale, and this is logarithmic scale. So, okay, so I'm going to talk about four different features which are labeled as A, B, C, and D. In going back in time, for example, this feature A is about 300 million years ago. The atmospheric CO2 concentrations were very low, okay, quite low, comparable to what we have today. They were quite low, just 300 million years ago. And so was the atmospheric temperature. So the Earth was much cooler, was cool, and the atmospheric carbon dioxide concentrations were low, and that was the time when the coal deposits that we have were formed. They were formed from the remains of trees. There was a lot of vegetation at that time. The carbon got preserved in the sediment, and so we had this spike in oxygen in the atmosphere. The oxygen concentration in the atmosphere had risen to about 32% at the time, 300 million years ago, called the Carboniferous period. And the temperatures were low, and so were the atmospheric CO2 content. Then we had time got B. It's about 55 million years ago. This is known as Paleocene Eocene Thermal Maximum, PETM. That's about 55 million years ago. The CO2 concentrations were quite high. In fact, and the earth was much warmer. And there are people who say that, there were times in the past when the earth was much warmer than it is today, CO2 levels are much higher. So it's a part of the nature's process, the earth will take care of itself. No, it's not true. We did not exist, the human beings did not exist 55 million years ago. Okay, and so the rate of change was much slower than what we are seeing today. So those are two important things. Okay, but this was a time when the CO2 concentrations in the atmosphere were high, and the earth was much warmer than it is today. That happened about 55 million years ago. After that, the concentrations of carbon dioxide. What did I do? The CO2 concentrations have been decreasing since after this 55 million years time frame, which is the PETM. There has been almost steady decrease in carbon dioxide concentration, and the earth has been cooling. This, by the way, was the time when the Indian landmass hit the Eurasian landmass, and the Himalayas were formed. And part of this decrease is, in fact, largely because of the weathering of rocks in Himalayas. As the Himalayas rose, there was increased weathering and carbon dioxide was consumed, and it started cooling down. So that was phase 2. Then we have C, which is orbitally posed glacial interglacial cycles, which are shown here in blue, and these are based on analysis of polar ice. I'm going to talk about it a little later. And then D is the steep increase in temperature and carbon dioxide due to human activities. And that is something that has happened only in the past 200 years or so. And that is something again that I'm going to be talking about. So the purpose of this slide is to show you the tight correlation between carbon dioxide and global atmospheric temperature. So the link is there. Now, how do you explain it? Okay, it also shows a dynamic system where the steady state occurs for short periods of time when inputs equal outputs. Okay, so the steady state which is maintained which can be maintained for short periods of time. And like I said, this long-term decrease in carbon dioxide concentration and in global temperatures is related to this weathering process where the rocks are dissolved and the carbon dioxide is consumed in this process. So this is weathering. The geologists are very interested in this process, and most of this decrease in carbon dioxide concentration and global cooling that occurred after the PETM is because of the Himalayas. The Himalayas the rise of Himalayas played a very important role in this change. Now let me talk a little bit about those energy balance, because that is what determines how warm the Earth is. We have two sources of energy on our planet. One is the sun. We get the radiation from the sun. And the other one is, that by the way is most important, the quantity of radiation that we receive, solar energy that we receive is huge. And so this is very important. The amount of radiation coming from the sun is the most important. Then we also have a smaller 99% of the energy comes from the sun. But there is also another source within the core of the earth, and that is the radioactive disintegration of compounds like elements like uranium-38, for example, and that generates heat. So as you will know, the Earth's core is very hot, and that heat drives the continent. So if you have an earthquake like we had last month, the energy for that comes from the Earth's internal heat. That there is convection within the Earth's mantle, and that pulls the continents apart or brings them together. That's a cyclic process. So tsunamis are generated by that, and earthquakes are created by that energy, which is the internal energy of the Earth. But that's only about 1%. 99% of the energy that we get on our planet is from the sun, and that's most important. Okay. Now, before I proceed any further, let me talk about two basic laws of physics, which I learned, by the way, in this department. The first one is the Stefan-Boltzmann law, and that talks about the black body radiation. The amount of radiation that black body emits is proportional to the 4 parts of the absolute temperature. I'm sure you all have. The other one is the Wien's displacement law. So it talks about the total radiation coming from a black body, emitted by a black body, and this talks about the frequency or the wavelength at which the radiation is emitted. And this says that the maximum intensity of the radiation will be at the wavelength, which is inversely proportional to the absolute temperature. So higher is the temperature, the lower will be the wavelength, and if the wavelength is lower, then the energy will be higher. Okay. So the sun is a very hot body, of course. The energy is generated through nuclear fusion. The temperature is very high, and therefore the energy that we receive from the sun is in the lower, is in the short wavelength and high energy. So that is what we get from the sun, because the sun is very hot. Okay? The temperature T is very high. So this parameter is high, so lambda will be low. Okay. And what happens? The radiation that we receive from the Earth is mostly emitted. Not mostly, about 30% is reflected from the top of the atmosphere, mostly from the top of the atmosphere and from the Earth's surface. 30% of what we receive from the sun is reflected back. 70% is absorbed, and then 70% doesn't remain. Okay, most of it is actually emitted back, but it's not emitted back in the same wavelength range, frequency range, because the Earth is much cooler than the sun, so T is low and lambda will be high. So the wavelength at which this radiation goes back is in the infrared range. It has low energy, long wavelength. Okay, so this is what goes back from the Earth's surface. Not everything is absorbed, but some part of it is absorbed by compounds like water, which are called greenhouse gases. There are species like H2O, CO2, methane, nitrous oxide, ozone, CFCs. These are the constituents of the atmosphere which absorb infrared in this way. Infrared because the vibrational their vibrational energy match with that bandwidth. So not everything is absorbed. However, there are certain bandwidth at which the or frequencies at which the atmosphere is transparent. So that radiation goes back into the space. Okay, it's not absorbed by any of the Earth's atmospheric constituents, but there are important bandwidths where there is strong absorption by water, by CO2, all these compounds. Okay, so these are called greenhouse gases. Okay, so the H2O, CO2, methane, nitrous oxide, ozone, CFCs, they all are important greenhouse gases, and because they are present in the atmosphere in high concentrations, they keep the atmosphere warm. Okay, by as much as 30 degrees Celsius, over 30 degrees Celsius, thereby making the Earth habitable. So had there not been these constituents present in the atmosphere, including water vapor, the Earth would have been much cooler, would not have been habitable. The temperature on an average of our planet, the planetary atmosphere, would have been lower by about 30 degrees Celsius. So they play a very important role in making our Earth habitable. By the way, these are cartoons which are very similar. This is qualitative, this is more quantitative. Don't worry about these internal things. What we should be concerned about are these fluxes. This is the total amount of solar radiation, which is 341.3 watt per meter square. That is the flux from the sun. This is what is reflected, which is 101.9 watt per meter square. And this is what is absorbed, what is emitted in the infrared range, and that is 238.3 watt per meter square. So if you sum up these two and subtract that sum from this number, you will get an anomaly of 1 watt per square meter. And that is because the concentrations of these compounds, particularly carbon dioxide, methane, and nitrous oxide, are rising. And that is due to human activity. Okay, so our activities are bringing these compounds, are releasing these compounds to the atmosphere, and the concentrations of this. So we have lost the balance that existed about 200 years ago. So the 200 years ago, the amount that was coming in was exactly balanced by the sum of this number and this number. It is not the case anymore. Okay, so we have disturbed it. We are retaining about 1 watt per square meter of radiation because of the increased concentrations of or increasing concentrations of these greenhouse gases in the atmosphere. The accumulation of greenhouse gases in the atmosphere has disturbed the radiation balance by about 1 watt per meter square, driving global warming. That is what we are worried about, and most of it is actually coming from this particular constituent, carbon dioxide. I'm going to talk about it in some more detail. So the greenhouse gases, of course, the most important greenhouse gas, by the way, is water vapor. Water vapor is present in concentrations about up to a few percent in the atmosphere in some cases, and but it does not control atmospheric temperature variations in the atmospheric temperature. It's the other way around. The temperature controls water vapor, how much water vapor remains in the atmosphere. The anthropogenic greenhouse warming is mainly due to non-condensable gases. Water is condensable, so as the air becomes loaded with moisture, it rises because it loses buoyancy, it rises. As it rises, it reaches altitudes which are cool, which are cold, so that water vapor comes out, it condenses. Okay, so it doesn't happen to carbon dioxide. The carbon dioxide is a non-condensable gas. So carbon dioxide, nitrous oxide, methane, they are all non-condensable, and they are the ones which are leading to greenhouse warming, not water vapor, because water vapor is condensable. So the changes in the temperature that we are seeing, not because of water vapor, but because of carbon dioxide to a large extent, but also to methane and nitrous oxide to a smaller extent. Okay, here is the list of these greenhouse gases. Carbon dioxide is the atmospheric concentration. In fact, the concentration has gone up. Okay. Since I prepared this slide last year, this was 417. Now this year it was 418. It reached new. About a month ago, last month in October, it was 418, and it's going to reach value of 425 by May next year, 24. So the concentrations are increasing. This concentration this was the concentration last year. Methane, here is the atmospheric lifetime. It remains in the atmosphere for periods ranging between 50 and 200 years. And the greenhouse warming potential is measured relative to carbon dioxide. So it's normalized to carbon dioxide. So obviously for carbon dioxide it's 1. For methane, the atmospheric concentration is 1.89 parts per million. The atmospheric lifetime is 12 plus minus 3 years, and the greenhouse warming potential is 21, which means that each molecule of methane is 21 times as potent in retaining the heat than carbon dioxide. In the case of nitrous oxide, it is 310. The atmospheric lifetime is 120 years. The concentration used to be 334, it has gone up. So goes for the other, these are synthetic gases. Hydrofluorocarbons, they are the ones which have replaced CFCs. Then perfluorocarbons, sulfur hexafluoride, these are all synthetic compounds which are used in refrigeration. Okay. You will notice that some of them have very high greenhouse warming potential. Each molecule of this SF6, for example, is about 24,000 as potent in retaining the Earth's heat, extra heat, than carbon dioxide. Fortunately, their concentrations are very low, and therefore none of these are quantitatively important as yet. The most important ones are carbon dioxide, methane, and nitrous oxide today. And among these three also, carbon dioxide is the most important. Okay, so these are the greenhouse gases, their greenhouse warming potential, and the concentrations. And I'm going to show you some data showing the natural variability in these some of these gases that happened in the past. I told you about the record of atmospheric carbon dioxide preserved in polar ice. So if you go to Antarctica and take a core here at this place, for example, this is Vostok. Okay, this place is called Vostok. This was under the control of Russians. So they did deep core here, collected ice core samples, and they analyzed different levels, extracted the gases which were preserved in these samples, and those gases were retained or trapped when the deposition of that ice occurred. Okay, so some of them are very old. If you go to the deepest sample, here is the age: 50, 100, 150, 200, 250, up to 425 kiloyears BP. So here we are talking about 4.25 lakhs years ago. And so these were samples taken from various levels, and they were the gases which were trapped in the samples were extracted and analyzed, and here is the record. Okay, so this is one of the major discoveries in earth sciences in my lifetime. After I joined NIA in the 1980s, this was a major discovery, one of the two major discoveries in earth sciences. This shows cyclic changes in the carbon dioxide concentration in the atmosphere, which relates to temperature changes. So delta T is the change in temperature, relative change in temperature, which is derived from oxygen isotope record. And overlaying on this is the carbon dioxide record, and you can see these cyclic changes that occurred in atmospheric carbon dioxide. And what was very remarkable was that the concentrations at the peak of the ice ages, these are the ones where the ice was most abundant on our planet, the atmospheric carbon dioxide concentration fell to about 190 parts per million. The last time it happened was about 21,000 years ago. This is the period. And so these are all the ice ages, the last glacial maximum, the glacial maximum before that, the one before that, and this is the last one that was studied. So we have this record of CO2 in blue, CO2 in red, and temperature in blue. They go absolutely, they are consistent with each other. So all these changes in temperature were driven largely by carbon dioxide, but also to some extent by methane. There is a similar record. This paper came in Nature. This is a record of methane in red, temperature in blue. So there were parallel changes occurring in methane. Methane concentrations, of course, were much lower than the CO2 concentration, but the trend of variability was the same. So this happened. This was discovered in this place, Vostok. This is the famous Vostok ice core, and subsequently another core was recovered from Antarctica, and that was from this Dome Sea side. This was even deeper, and they could go back to about 800,000 years, 8 lakh years in time. They also added nitrous oxide in this study, and again you can see these cyclic changes that occurred on time scales of about 100,000 years. These are glacial changes. Every 100 years the ice sheet builds up, the sea level goes down to by about 120 meters, and then suddenly there is warming, so these cyclic changes, these are interglacial periods, which are very short, typically of about 10,000 years duration, and this is the glacial maximum. So there is a gradual build-up of ice and sudden collapse. This is a pattern which has been repeating itself in the last 1 million years. Okay, so this is something which was discovered during my career. There was a lot of activity, number of papers came out to explain these phenomena, but there's not, even today, there is still controversy about what exactly drove these changes, although everybody agrees that it has something to do with the oceanic circulation and biochemistry. Okay, let me talk a little bit about high resolution changes in the past 2,000 years. Okay, for the last 10,000 years, this is the glacial period, interglacial period, the last interglacial period, the climate of our planet has been very moderate and consistent, constant. Okay, the CO2 concentration has been very constant, as you can see here. CO2, methane, blue one, nitrous oxide, here are the scales. CO2, 250, it was 280. For most of the period, it was 280. Okay, and then it started rising about 200 years ago, at the turn of the 19th century. When the industrial revolution took place, around 1850s, 1860s, began to rise. First slowly, and then it's rising very rapidly because we are releasing a lot of carbon into the atmosphere and methane and nitrous oxide to the atmosphere due to human activities. So you can see this hockey stick record, which also goes well with the temperature changes. So that only occurred in the last 400 years. Prior to that, for about 10,000 years, at least 10,000 years, the atmospheric carbon dioxide concentration had been remarkably constant. And the temperatures were very, very mild and constant. This allowed the development of civilization that happened in the last 10,000 years. I am presenting here only the data for the last 2,000 years. Okay, here are the instrumental changes, instrumental records that were initiated by a person called Charles Keeling in University of California, San Diego, Scripps Institution of Oceanography. He set up a facility for continuous measurements of carbon dioxide at a place called Mauna Loa. This is a place in Hawaii. So he established this record. It's called the Keeling curve. I had the privilege of spending a week with this gentleman way back in 1994. You can see the changes in carbon dioxide concentration, continuous increase. This record goes back to 1958, from the time I was 4 years old. This record has been continued. It's called the Keeling curve. What is remarkable about this record is it was something that was not expected, was these cyclic changes that occur on a seasonal scale. You can see these oscillations. You get a maximum concentration during the early spring, late spring actually, sometimes in May, and then the concentration goes down to a minimum in October, rises again, reaches a maximum in May, falls again, and this is a seasonal trend. And this seasonal trend was explained by Keeling to changes arising from asymmetric distribution of landmass. So in summer we have longer growing season and there is more landmass in the northern hemisphere. So in summer there is a lot of carbon dioxide taken up from the atmosphere by biota. Okay, so it brings down the atmospheric carbon, but this actually happens, it starts happening in May, but the decrease starts happening in May. You should not, and the minimum that you see, and the minimum this year was in October, when the concentration was 218 ppm. Okay, it's not given here. I have data only for last year. I was teaching a course in IIT Kanpur and I had prepared this slide here. I did not update this slide, but it reached a value of about 218 here, minimum of 218 this year. And this rising today is 418, today is 421 as of today, 421.5. You can go back to this, this information is available on the internet. You can log into this and get this information. So these changes that you see are related to asymmetric distribution of landmass on our planet, such that we have more landmass in the northern hemisphere than in the southern hemisphere. So here we are seeing a signal of that. Okay, so this is something that was, these are the mean changes that the curve there is a consistent increase that you see which overlays the seasonal, which includes the seasonal change. Okay, so that was for carbon dioxide. We get a similar trend for methane as well. So if you look at the methane, there was actually a hump. People are not able to explain. Sometimes around this was around 2000. Yeah, that was the time when methane kind of leveled off. Okay, it was not changing. People are still discussing why it happened, but then the trend picked up. But there is a long-term increase in methane as well. And the growth rate is 11.3 parts per billion per year. And you also see the seasonality in much the same way as we see in carbon dioxide, we also see in methane, because methane also has a biological source. Okay, so whenever you have a biological source, whenever it has to do something to do with biota, you will see these seasonal changes. Also see this to some extent in nitrous oxide, not to the extent that we see in the case of carbon dioxide, methane, but there is also a seasonality. Okay, that's better mark here. Okay, so the growth rate is 0.75 ppb per year. It's important because N2O is 300 times more potent than carbon dioxide. And finally, if you go to these SF6, which is synthetically produced, we don't see any biological seasonality because the source is not biological. So there is no seasonality in case of SF6. SF6 concentrations are much lower. It's actually pp trillion it is not. We often write pptr, so I made a mistake of not doing that. PPT is parts per thousand, PPTR is parts per trillion. Okay, so this is for SF6, the concentrations are much lower. Okay, so these are 3 orders of magnitude lower. So even though it has a much higher greenhouse warming potential, the concentrations are very low. Okay, so most of the greenhouse warming that we see, the greenhouse warming, the variability that we see, the increase in the atmospheric temperature is because of carbon dioxide, largely because of the emissions. This is the blue portion, this is the emission, this is the contribution from deforestation. Okay, so we are decreasing the source, the flux into the biota and methane. So these carbon species, carbon dioxide, and that's methane, they together contribute to about 92% of the greenhouse warming. The greenhouse warming that we are seeing is 90% because of carbon species, 6% because of nitrous oxide, and 2% that's important. Carbon is so important, both in the form, primarily in the form of carbon dioxide, but also in the form of methane. So what are the sources of carbon dioxide? Organic matter decomposition, fossil fuel consumption, land use change, is deforestation, industrial activities, particularly the production of cement. Okay, so these are the sources of carbon dioxide. In the case of methane, it's produced under anoxic conditions through 2 pathways. The acetate fermentation is fermentation rate, not oxidation, or like acetic acid will give you carbon dioxide and methane. And there is the other process is the reduction of carbon dioxide. This happens in the freshwater environment, this happens in the marine environment, and we also have sources coming from agriculture. Rice paddies are big contributors. Wetlands, by the way, I am working on some of these wetlands right now. Landfills and livestock, the enteric fermentation is a big producer of methane. In case of nitrous oxide, we get the production occurs through denitrification, and nitrification is something I am not going to go into detail because this is more specialized. But that's something that I work on the nitrogen cycle. So I will skip this because even though it contributes to about 6% of the total greenhouse warming, it's not important in the context of today's problem. Now let me briefly talk about the change between the difference between the climate variability and climate change. Now, we Indians can be forgiven for this because climate has only one Hindi translation, Mausam. In Hindi, we have only Mausam. For weather, we have Mausam. For climate, also we have Mausam. But actually, they are not the same. Mausam is not, climate is not Mausam. weather is so we can be forgiven. It's like kal is yesterday is kal and tomorrow is also kal. We make that kind of a mistake. Okay, so like I will be going. I had gone there tomorrow. We will translate from Hindi to English. So that's the problem with this as well. So when we talk about weather and climate, they are basically different things, as I'm sure you all know. Weather is something that actually lasts for hours, days, and probably also months. Okay, that's the weather. Like yesterday was warmer than today. I'm talking about weather. I'm not talking about like President Trump. I'm not talking about the climate. When I say this year is going to be cool, it doesn't mean that there is a climate change. Okay? So he once said that we could do a little bit with global warming because that particular year was very cold year in the US. But that's weather. Climate is very different. Climate is a long-term condition. Okay? It operates on time scales of decades to centuries. And then we have climate variability, which is from months to decades. So when you see variability, climatic variability, natural variability, so there are various features, various phenomena that occur and that are related to this time scale, or they should be interpreted with this background. For example, a rainstorm occurs on time periods of hours. Okay, a tropical cyclone on time periods of few days. Wet season, dry season, the season changes we have. The monsoon, for example, is on time scale of days to months. Okay, El Nino and La Nina, they occur on time scales of years. Maybe 2 to 5 years we have this phenomenon. And that is for the Pacific Ocean. In the Indian Ocean, we have Indian Ocean dipole. In the Atlantic Ocean, we have Atlantic meridional oscillation. These are climatic modes. Okay, and we also have in Pacific, so we have Pacific decadal oscillations. So these are natural changes in the climate, like El Nino. El Nino is not man-made; it's a natural phenomenon that occurs once every 2 to 5 years. Okay, so that is climate variability. And that must be differentiated from the climate change. So this is one major area where there is a lot of disagreement. You say the side trend of warming in the Indian Ocean in the last 20 years. Somebody will say, oh, it may be a part of the natural variability. Okay? So it's very hard to differentiate between I'm sorry. So it's important to differentiate between the climate change and the climate variability. And a lot of people who actually question the climate change say that whatever is happening or whatever we are observing is a part of natural climate variability. And there is an example of this in the temperature record that we have of changes that occurred in the last few hundred years. And we see changes in this temperature versus time in the last how many years? This is from this 2000, present 2020, and this is 200 years ago. This for last 200 years. Sorry, 200, 400, 600, last 2000 years. Yeah. Okay, so, but you can see these changes in the meridional, in the temperature which are related to changes in the in the changes in there's the natural variability in the climate. Anthropogenically caused climate change must be distinguished from natural variability. I just said that. Here are some projections for the future that show how the climate is going to change in the future in relation to changes in the carbon dioxide emissions to the atmosphere and the different scenarios. Here is what we have so far, and we can see a tight relationship between the changes in the atmospheric temperature versus the total amount of carbon that we have released to the atmosphere, and we see this linear relationship. And in the future as well, the atmospheric temperature will continue to rise. To what extent will depend upon the rate at which we are emitting the carbon to the atmosphere. There is under different scenarios of climate change. But under the worst case scenario or business as usual, the Earth is going to be warmer by at least 2 degrees by 2050. I think that's all I have to say. I have another slide that gives the conclusions. Human-induced climate change is real, already being manifested by frequent disasters all over the world. Although anthropogenic carbon dioxide concentration and temperatures were higher in the geological past than they are today, the rate of change was much lower, and importantly, there were no human beings to suffer. The ongoing changes are directly caused by the rising atmospheric greenhouse gas content, mostly carbon dioxide. Their emissions must be curbed through population control and utilization of renewable energy. And the global climate change is not the only adverse consequence of human activities. We must also consider other stresses such as acidification, eutrophication, deoxygenation of water bodies, some of the things that I am working on right now, and other forms of environmental pollution. And this is going to have a large impact on ecosystem, biodiversity, global elemental cycles, and human health in the future. Something that we do not know much about right now. Thank you very much.